another terminology, directional derivative. Okay? So again, when we're given a function f of x, y, the directional derivative of f in the direction of a unit vector is defined this way, okay? So d lower u f is the name, okay? So this is just a name of the derivative. Just like in calc 1, we write f prime of x as a derivative of the function, right? Okay, and the directional derivative can be obtained or defined through this formula. So first of all, remember when we have a function, we can talk about gradient. So this is gradient f, and what is that? This is a vector. Okay, u is given as a vector because that's a vector that gives you a direction. All right, so here's the formula. That's the algebra. It's a formula you need to memorize for finding directional derivative. I want to look at the geometry a little bit. So when I have a function z of f of x, y, I know in three-dimensional space, this gives me a surface like that, for example, okay? And in addition to that, I'm given a direction, u, and I want this u to be of length 1, so it's a unit vector. All right, so if I extend this direction, on the xy plane, this is like what you see, right? Okay, so now suppose you have like a very big knife and just cut this through along this direction. So what you see will be a cross section like this on the surface, okay? So this green curve sits right above the blue line, okay, and it's on the surface. Okay, so now if I restrict f in the direction of u, I only see this part, this curve, right? Okay, so the directional derivative is asking, okay, suppose I only care about this green curve. What is its derivative? Okay, and this is similar to what do we have in calc 1? So calc 1, when we have only one variable, we have a curve like that, right? And at each point, we can talk about the derivative. And the derivative gives you the slope of the tangent line, for example, like that here, right? Okay? And now it's just imagine we are still trying to find derivative of a curve. But now this curve is not sitting in R2, it is sitting in R3. Okay, it comes from a surface restricted onto a straight line. And what is the line? That is the line determined by a given vector u. Okay, so when we talk about directional derivative, I always need to give you two ingredients, otherwise I cannot talk about directional derivative. First of all, you need to give me the function, so I know which function I'm working with. It's a derivative of which function. Second, you need to tell me which direction you are looking at. So then I will restrict the surface onto just a curve that's traveling along the u direction. So you need to give me the u in order to say what is the directional derivative of f in the direction of u. So when we talk about directional derivatives, these are the two ingredients you must have. Without one of these, you won't be able to find the right answer. Okay? And this formula tells you how to find it. Let me give you a quick example. So, find the directional derivative of z equals f of xy equals, let me erase this. Equals square root of x squared plus y squared. Okay. In the direction of u equals 1 over root 2, 1 over root 2. Okay? So, I'm gonna first check if if the length of u is equal to 1. Okay? Because remember, we need unit vector in our formula. So let me go ahead, find length of u. So that's 1 over 2, 1 over root 2, 1 over root 2, square root of 1 over root 2 squared plus 1 over root 2 squared. This is equal to square root of 1 over 2 plus 1 over 2. Good, that is equal to 1. Square root of 1 is equal to 1. All right, so now we're good. 2. Find gradient f. Do you still remember what is the gradient f? The formula for gradient f is df dx I plus df dy j. Okay? So this is f of xy. Find its gradient. df dx. Okay? So this is a composite function. Square root is outer function, x squared plus y squared is the inner function. 1 over 2 x squared plus y squared to the power minus a half is the derivative of the outer function, evaluated at the inner function. Okay? Times derivative of the inner function. Because in the eyes of x, y is a constant, so derivative of y squared equals 0. Now put this together, cross out the 2, I have x over square root of x squared plus y squared as my df dx. Similarly, df dy is equal to 1 over 2 x squared plus y squared to the power minus a half. Derivative of the inner function with respect to y this time gives you 2y. Cross out the 2, I get y over square root of x squared plus y squared. Okay? So 3, the directional derivative of f in the direction for u is gradient f. So that's this vector. Right. So this is a vector, even though it's a vector value, it is still, even though it's a function, but it is still a vector. That the unit vector 1 over root 2, 1 over root 2. Okay? So we have vector that is vector. Now it gives you x over root 2 times root 2 x squared plus y squared plus y over root 2 times root squared x squared plus y squared. Okay, so here you get a scalar, and this scalar has a geometric meaning. It represents slope, right? Just like how we find f prime of x, and f prime of x is slope. Let me see if you can see. Yeah. Okay. All right. And this just means when I have a surface, so the surface of this guy is a upper hemisphere, like that. Okay? And in the direction of, this is x, y, z. In the direction of root 2, so that's this direction. So I have a curve like that on the upper hemisphere along the direction u. Okay? So now you can say at any point that's on this curve, just plug in the x and y values into this formula, then you will be able to find, oh, the slope of this tangent line is equal to this much over this point. Then you say, you plug the x and y values into this formula, then you say, oh, the slope of this tangent line is that much. Okay?